Okay, this is the second part of the basics of memory, and what we're going to talk about first of all is what a memory address is. So in this example we have 1K byte of memory, so remember that means we have 1K or 1024 registers, and each register can hold 8 bits, right? Because again, a byte is 8 bits. So this is the notation that we have. Again, each rectangle is a register, and excuse me, each square inside the rectangle that represents the register is a memory cell. And since we have the word byte here in the description, each one of these registers can hold 8 bits. Well, a memory address is just a unique number assigned to a register. Okay, so let's write that down because sometimes there's confusion about this. Okay, address is unique that's assigned to each register. And we always start with address 0. So this first register will have address 0, and then we just go 1, 2, and this is going to go all the way up to the 1024th register. Well, since we started with an address of 0, the address of the 1024th register would be 1023. Okay, it's going to be one less than this number here because we started with an address of 0. Well, these would be the base 10 addresses, but as you know, in the digital world we deal with base 2, so on a circuit board or in a digital circuit, these addresses are represented by zeros and ones. So one way to find the number of bits that you need in order to have enough for your maximum address is you just find what whole power of base 2 gives you the number of registers. So if we just take the number of registers, okay, and set it equal 2 to the n, well, n here will be the address bits. So if you take 1024 in our example and you solve for n, you'll see that n comes out to 10, that we need 10 address bits. So the maximum address, the 1023 here, is when all the bits are equal to 1. Okay? And you know, of course, this would be when all the address bits are 0. Right, and then we'd have all zeros and a 1, and then all zeros, 1, 0, and so on. Okay, just like, you know, binary code. So that's all an address is, right? It's just a number assigned to each memory register inside the memory IC to distinguish one register's contents from another, right? Because typically these registers are going to be storing different strings of zeros and ones because they're going to be storing different data, and we need a way to distinguish between those registers. So just a couple other examples here before we talk about memory cells, and that's if we had, okay, some examples here. Okay, say we had 64K byte memory. Okay, how many address bits? Okay, well, again, all you have to do is take the number of registers, which would be 65,536, set it to 2 to the n, solve for n. Another way is, since we know that 10 address bits is enough to address 1024 registers, and also we know that anytime we add a bit, we double the number of values, right? That's just the general base 2 concept we went over, you know, quite a while ago. So every time I add an address bit, that doubles the number of registers I can address. So since 10 address bits allows me to address 1024 registers. If I add one address bit to 11, that would be 2048 registers that I could address, okay, or 2K. 12 would be 4K, 13 would be 8K, 14 would be 16K, 15 would be 32K, and 16 would be 64K. Okay, so there's different ways to come up with the answer, but you should get comfortable with determining how many address bits you need for a certain number of registers of memory, or registers inside memory. Now here's a little tricky one. What if we had 64K 16-bit? Oops. Shouldn't be an I, sorry about that. 16-bit memory. You know, how many address bits would that memory IC need? Okay, and this is tricky because sometimes people are fooled into thinking, well, since this is 16 bits and prior we had 8 bits, that somehow the answer is different. But you see, it would still be 16 because addresses have to do with the number of registers. It has nothing to do with the number of bits that each register is storing. So, you know, if I had each rectangle here representing the register out with 16 squares, because it can store 16 bits, it doesn't change the number out here. It doesn't change the total number of addresses. In fact, it doesn't change it at all because we still have the same number of registers. Alright, well, let's finish up memory with just talking about some different types of way of storing bits. And these circuits that can store bits are called memory cells. Now on PolyLearn, there's this handout that goes over all the different types of memory, talks about RAM and ROM, which I would imagine a lot of you are familiar with, having grown up with computers. So I'm not going to read to you what's on this handout. You can read it yourself. But I do just want to talk about a portion of what's on this handout, and that's the memory cells. You see, up to this point, we've just talked about D flip-flops that make up memory registers, and you know, we've discussed this. Now, you'll see on the handout that this type of memory that uses flip-flops is called static RAM. Okay, so static RAM uses flip-flops, and you know, static RAM, this type of memory is what you find in cache memory, okay, that some of you may be familiar with. That's memory that is located close and operates at a frequency, you know, just below the microprocessor frequency. So it's fast memory. But another way that you can store bits is just with the use of integrated capacitors. And this type of memory that uses integrated capacitors is called dynamic RAM. Okay, and that's the memory that makes up most of your working memory inside your computer. So simply what we do here, or what's done here, is that when this integrated capacitor is charged, well, then it's storing a 1. If it's not charged, right, if there's 0 volts across it, well, then that's how you store a 0. Okay, so dynamic RAM, you're just using integrated capacitors, silicon capacitors, to do the storing of the bits. And the handout talks about the advantages and disadvantages of both of these. Okay, this circuit over here, which is a BJT switch, okay, that we covered earlier this quarter. Well, this is the memory cell for a basic ROM, okay, read-only type of IC. And the way that the bits are stored with this memory cell is just by doing what we call a hardwire. Okay, if we hardwire, which is just a term that means short, okay, if we short the input of this transistor switch to ground, okay, that's going to make Vn equal to 0, which makes an open. Okay, this is material we've covered previously, right? We'll get an open between collector and emitter, okay, which means no voltage drop because no current through this resistor at the collector, which means V out just equals VCC, which is a 1. Now, if we hardwire or short the input of this transistor switch to VCC, okay, like this, well, that's going to make this input equal to VCC, which is going to make the collector to emitter a short, and that's going to ground V out and make V out a 0. Okay, so you see that's how a 0 is stored with this memory cell. So you see, just by either shorting the input to ground or shorting the input to VCC, we can store either a 1 or a 0. And these hardwires, they're done at the time that the integrated ROM IC is manufactured. So the manufacturer actually is the entity that puts these hardwires or these shorts into our circuit here to get the appropriate data that we want at V out. Okay, well, you can read more about these different types of memory on your own. And then the last video of the quarter will just be a short video on an overview of a microprocessor.